Welcome back. In this video we're going to be talking about Hooke's law. So again, Hooke's law is vitally important for a huge bunch of physics. It helps to explain how things move. So, in the last lesson we talked about F is equal to ma. So if I have a force on something, its acceleration is equal to that force divided by the object's mass. So if I have somebody here, I can use force arrows here to show the forces on something. So I've got a big force acting downwards and a small force acting upwards. And this is an object of mass m. What will happen to it? Well, from F is ma, I can say that there will be an acceleration, and that acceleration is going to be downwards because I've got a force, big force acting down, only a little force acting up, and it's acting on a mass, so that mass is going to accelerate downwards. Here, I've got a big force acting up, small force acting down. So what will happen to it? Yeah, it's pretty simple. This time it's going to accelerate upwards. But here's something interesting. This is not my cat. My cat was wandering around, but she's escaped. So if she comes back into shot, I'll show you my cat later. But this cat loves to cuddle a teddy bear. And when it cuddles it, it's applying a force to it. So there's a force between the cat's paws on the teddy bear. But it doesn't accelerate the teddy bear. The teddy bear doesn't start to move. What happens? Well, a force can actually change the shape of something. And in today's lesson, we're going to be thinking mainly about springs. So the real key thing to get is that forces don't just affect the movement of objects. They can also affect their shape. And you can see that here. If you just squeeze a sponge, the sponge changes shape. If you knead dough, you're putting in a force and you're changing its shape. And same thing with a spring. If I push on the end of my spring, if I apply a force to the end of the spring is going to end up more compressed and taking up a smaller length. So that's all about Hooke's law. So in class, you're going to do a really simple experiment. You're going to have a spring, and you're going to hold it on a clamp stand, and you're going to attach different masses to it. Now, in a future lesson, we're going to work out how we're going to go into details about the force that is going to apply. But basically, that means that I'm going to be stretching my spring. And what you'll be doing is you will be measuring the length of the spring, and after that's been done, you'll get a slightly longer spring. Whoops. So it will look something like this. Yeah, because it's got longer. And what you'll be interested in is the increase in length. So if this was my original length, now it's got longer, and we're going to call that delta L. So that funny little triangle symbol is called a delta. It's a Greek letter, and it means change in. So you're going to measure the change in length, or delta L. Now we call delta L an extension. So it's just a measure of how much longer has my spring got. Now, in science we love to see how one thing affects something else. So what we're going to aim for is a graph where we can have our force applied on one axis and our extension along the other. And what you'll find during this experiment is you'll get a graph that looks very similar to this. It will, when you plot your points, you'll find they'll go up and up and up and up and up. And for you, they'll just go all the way up because you're not going to murder my springs. If you did murder your springs, though, what you'd find is after a while, the springs don't carry on extending anymore. Instead, the spring starts to do this strange thing where it becomes straight, it starts to bend and the curve goes off, like you can see in the diagram. And we call that the elastic limit. So that's the point where something no longer acts like a spring and starts to be permanently damaged. For GCSE, that's all you need to know, is just that this bit is the normal section, this bit is beyond the elastic limit. So one of the cool things about physics is we love to do a little bit of maths. And a bit like I did with the forces, mass times acceleration, we can apply this to a graph. So this is only going to work for the straight section. So just thinking about the straight section, there's an A somewhere in straight, we're going to think about how the stretching force, which I'm going to call F, is proportional to the extension, which I'm going to call big E or little e. I'm going to call it little e for now. Sometimes you'll see it as little e, sometimes you'll see it as delta L, and sometimes you might see it as big E. It doesn't matter, it's just you need to use the right term. You just need to use whatever term they give you in the exam board, and they do sometimes change it around. So let's think about an ordinary graph. If I have an ordinary graph of y and x, and it's got a gradient, or a line that looks like this, what would be the equation of this line? Hopefully you will remember that for a straight line, we can say, if that's the gradient m, it's got the general equation of y is equal to mx plus c. This works for any graph. Well, does it really matter if I label this axis y, or if I label it this one x, or can I give it a different letter? And it turns out it doesn't actually matter what letter I give it. So what I can say is for this straight section, it has the equation f is equal to the gradient m times e plus a constant. So it's exactly the same. Yeah, all I've done is replaced y with f, because this graph doesn't have a y-axis, it has a force axis, and I've replaced my x with e, because it just doesn't have an x-axis, it has an e-axis. Now looking at this graph, what is c? If I look at it, I can say c is 0. So straight away I can say force is equal to me, and plus 0 just drops off, it just disappears. Now, this gradient here is a constant, and it's a property of the spring, and I'm going to call this gradient something's spring constant, which is the gradient. And I'm going to give it the letter K. Don't ask me why, physicists are weird. So my final equation is going to be the force on my spring is equal to some constant multiplied by the extension of the spring. Yeah, and I just label those. So this is the force, this is the spring constant, and E is my extension. Now taken together, this has an important name. This is called Hooke's law. And it tells us that the force on an object is equal to its spring constant multiplied by its extension, or we can say that if we want to know how much something is going to extend, I can say the extension of a spring is equal to the force acting on it divided by its spring constant. So all springs have slightly different Hooke's law graphs, and they all have different elastic limits. And we give it a number based on its stretchiness, called the spring constant. Now if you look at this, this is a force divided by, I can say, let's rearrange it. I can also say that spring constant K is equal to force divided by extension. Now force has the units meters, no it doesn't, force has the unit newtons, and it's being divided by something that has the, sorry I'm just checking my thing's still running, I had a horrible worry for a second, that wasn't recording. Force has the units of newtons, and I'm dividing it by something that has the units meters, because I'm doing an extension in meters. So K has the units newtons per meter. That's going to be important for later. So the stretchier the spring, or the easier to stretch, that has a lower K. The stiffer the spring, a higher K. And if you think about it, that makes sense, because what this is saying is how many newtons do I need to make it stretch by a meter? So if I need lots of newtons, that means I've got to put in loads of force to stretch it. If I don't need many newtons, I don't need much. Here's some questions then. Which one represents a proportional relationship? We talked about Hooke's law being a proportional, so which one of these is proportional? This is this one. If you were to write it as an equation, you would say A is equal to some constant times B, the gradient times B, and in this case m is 1, so you can just say A is equal to B. A bit A-level-y, but worth thinking about. What does Hooke's law state? So Hooke's law is force on a spring is equal to... No, I'm not going to write it that way. Yes, I am. I'm going to say force on a spring is equal to its spring constant multiplied by its extension. You need to identify... If you're ever given this question, you need to say what each of these terms mean. If a spring stretches 20 centimeters with 1 gram on it, based on Hooke's law, what length will the spring be with 20 grams on it? So this is quite cool. So initially, I'm saying that this will be my extension, and this will be my force. Well, this won't be a force, this will be a mass. And it's quite an evil question, because I need to know from what mass do I get a force. So 1 gram, 100 grams gives me 1 newton. So 1 gram, that will give me 0.01 newtons. So I can say that F is equal to KE. So I can say that 0.01 is equal to K times 20 centimeters, because I can leave it in centimeters, that's not a problem. So I can say K is 0.01 divided by 20. So K is 0.0005 newtons per centimeter. I can use it that way. And then I'm going to plug it back into the equation. So now my force will be 0.02 newtons. And that is going to be equal to my spring constant, which is 0.005. Multiplied by extension. So extension will be 0.02 divided by 0.0005. I should have picked better numbers for this question, which comes to 0.02 divided by 0.0005. That is 40 centimeters. You may have been able to see that from the question. I've doubled the force, therefore I'll double the extension, but it's always nice to show how to do it properly. So when the graph has this reached its elastic limit, for those of you playing along at home, I'll give you 3 options. Let's call that A, B, C, D, and E. Where's it reached its elastic limit? It's here. So one thing I didn't go into, let's just talk about it now. In this section, over here, it is obeying Hooke's law. Okay, beyond that point it no longer obeys Hooke's law because it's past the elastic limit. And in what real world context is Hooke's law important? You can think of bungee jumps, car springs, anything that involves a spring moving. Okay, next lesson we're going to be talking about falling under gravity. I'll see you then.